Kelp is a crucial marine resource that provides habitat, sequesters carbon, creates oxygen, and removes excess nutrients from the ocean, preventing harmful algae blooms worsened by climate change and human activity. Kelp is used in organic plant fertilizers, animal feed, and cosmetics, and it can also be eaten. However, climate change has made it harder to farm kelp. Kelp grow best in cold water and are particularly sensitive to warmer temperatures, which can slow their growth or outright kill them. Due to the impacts of climate change, increasing global demands for kelp will not be met unless we can find a way to make kelp farming more resilient. Using a technique called selective breeding, we can speed up kelp's ability to adapt to warming waters and make kelp farming a viable commercial opportunity today.
Humans have been selectively breeding crops for thousands of years, and it is a widespread agricultural technique. When you buy produce at the store, almost everything has been selectively bred to make products that are more nutritious, taste better, and grow more easily. Selective breeding works by pairing individual parents with traits desirable for human cultivation and consumption so that their offspring inherit these traits. In the last 60 years, selective breeding has helped improve the efficiency and resiliency of crops, which has led to reduced hunger, reduced poverty, and more efficient land use for agriculture. Though the history of selective breeding is long, humans have only been selectively breeding kelp in the last 70 years. Recently, we've been able to use a technique called molecular breeding to accelerate how quickly kelp displays desirable traits like higher yield and increased thermal tolerance. By increasing yield, we can grow more kelp in less space, which lowers the overall cost of production. By increasing thermal tolerance, we can extend the growing season for kelp and improve their resilience to warming ocean temperatures. Advances in genetic sequencing have greatly benefited selective breeding efforts. We can now analyze a kelp's genome and predict how well it might perform in a farmed environment. The genome is a blueprint for all biological processes like growing, adapting to stressful conditions, and surviving. Molecular breeding looks at how specific regions of the genome influence biological processes important to the farmer, like growth, stress response, and reproduction. This benefits selective breeding efforts by identifying key regions of the genome that can improve farming. For example, instead of having to wait and see what kelp grows well, we will be able to predict which kelp will grow well based on analyzing their genome and comparing it to other kelp. This will save a lot of time and improve our efficiency and our accuracy in breeding improved kelp. Over a long time and many generations of breeding, these improved farm kelp may become significantly different from wild kelp. Currently, this is not a concern due to breeding research being in such an early and limited phase, but in the future, this may be an important consideration. Across aquaculture, there has been a focus on practices that protect ocean ecosystems from farmed individuals that have the potential to be invasive. One solution has been to use non-reproductive kelp individuals so that they don't pose a risk to the environment around their farms. We want to make sure kelp farming is safe and sustainable, so we've developed methods to reduce any potential interactions between our selectively bred kelp and wild populations. First, farm kelp can be grown far enough away from wild beds to protect marine ecosystems. And second, we can make farm kelp non-reproductive using molecular breeding techniques aided by our analysis of the kelp genome. This would ensure that farm kelp cannot mix or breed with wild kelp. So how do we do this? When we began our breeding research, we brought different wild kelp plants to a farm environment to test how quickly they grew, how heat tolerant they were, and how many nutrients they took from their environment. We predicted that we could generate a new phenotype called non-reproductive kelp using the genetic resources established in our initial breeding project. We then used genomic analysis to predict which kelp parents should be paired so that their offspring would be sterile, like how a horse and a donkey can both be fertile, but their offspring, the mule, cannot reproduce. This process is non-GMO because it does not involve gene editing and instead relies on existing natural genetic diversity in kelp, where some of them cannot reproduce. We can verify that our molecularly bred kelp are non-reproductive in 4 ways. We first look at our non-reproductive kelp and make sure that they have not physically developed reproductive tissue. We then put the kelp in a laboratory setting where we play with light and temperature conditions that should encourage the kelp to try to reproduce. If the kelp does produce offspring or spores, we look to see if the offspring are viable or capable of reproducing. This multi-step validation process can take a long time, so we have also developed PCR tests to confirm that essential reproduction genes are not functional in our putative non-reproductive kelp. So in total, we have 4 ways to validate that molecularly bred kelp are non-reproductive: by monitoring their physical development of any reproductive tissue, attempting to induce reproduction, confirming any produced offspring are not viable, and finally, with molecular tests. Kelp farming provides tremendous environmental and economic benefits globally with its varied applications and uses in numerous products. Selective breeding is a technique that has seen great success in agriculture, and we hope to have even more efficient results with molecular breeding to increase the potential of kelp aquaculture in the United States and bolster the domestic marine industry.
Over the last 30 years, aquaculture has grown to meet increasing global demands for ocean food products. The effects of climate change have made it more difficult to grow kelp due to their sensitivity to warming ocean temperatures. This limits how much kelp can be grown for applications in agriculture, pharmaceuticals, and direct consumption. Selective breeding of improved farmed kelp is one new, promising approach that supports the expansion of kelp aquaculture to be environmentally safe, resilient, and profitable.